Programming quadruped robot to walk forward and backwards, do rotations and climb slopes using ROS2 and Isaac simulator. Outline. In this video, firstly, robot capabilities will be demonstrated. In other words, I will show what robot can do. And next, programming methodology will be explained. Graphic user interface of Isaac simulator is used for running simulations. Here you see a screenshot of Isaac simulator graphic user interface. You can see a stage with robot and also 3 slopes on the stage. In the following demonstrations, I will run simulations using graphic user interface, but I will use full screen mode for displaying results, so only stage part of the graphic user interface will be shown. Robot is steered by Sony PlayStation PS4 controller. Also, graphic user interface based controller developed using Qt software is also provided, so people who do not have PS4 controller also can do simulations. Now I will demonstrate what robot is capable of doing. Firstly, robot can walk forward. It can walk slowly and it can walk very fast. Speed of robot is controlled by PS4 controller. Robot can walk backwards. In a similar way, it can walk slowly and it can walk fast. Robot can do rotations. Firstly, I will show leftward rotation while walking forward. And now, rightward rotation. You cannot make robot rotating fast by using controller. This is because inertia force prevents robot from turning very fast. Okay, and robot also can do rotations while walking backwards. So robot can do rotations leftwards. In a similar way, speed of rotations when walking backwards is almost not controlled by PS4 controller, just slightly. And now rightwards rotations when walking backwards. Okay, so now you see three slopes in front of robot. Robot now is approaching the slopes. So let's try. If robot can climb slopes, and firstly robot will try the green slope. I need to zoom out to display all slopes, and also I will move slopes to the center of the stage view. Okay, so now robot is ready to climb. Okay, so robot successfully climbed the slope. And why not to try to go back in the same way? Okay, so robot successfully managed to do it once again. Right now you observed how robot needed to make significant effort to ascend the slope, and also how it was sliding down when descending. So this means significant gravitational force, large gravitational force acts on the robot. And considering this, climbing blue slope seems like an unreasonable task. However, you see robot now assuming the initial position to climb the slope, blue slope. So, okay, even it seems an unreasonable task, why not to try? I will zoom in before robot tries to climb a slope. Okay, as you can see, robot successfully climbed the blue slope, and now is turning back to return on the other side of the slope in the same way. Okay, robot managed to get back by climbing blue slope, and this ends demonstration of robot capabilities. Next, I will explain how to use controller based on graphic user interface if you don't have PS4 Sony controller. In the preceding demonstrations, I used Sony PlayStation PS4 controller. If you don't have PS4 controller, you can use graphic user interface based controller. Later I will explain how to launch the controller, and after launching you can place it where you like. Usage of such controller is self-evident. There is large red circle and small black circle inside red circle. So if you move black circle upwards, robot will start moving, and as black circle approaches the edge of the right circle, robot will move faster. If you move black circle downwards, robot will walk backwards. And also, with black circle approaching the edge of the red circle, robot will walk faster. Next, it is possible to do rotation using this controller. For rotations, when robot walks forward, you need to place black circle at the right edge of the red circle, and black circle should be slightly higher than center of the red circle. Okay, so now robot finished rightwards rotation, and now it will make leftwards rotation. Robot also can do rotations when walking backwards. So this is leftward rotation. And next is rightwards rotation. Note that speed of the rotations, either when walking forward or when walking backward, speed of the rotations cannot be changed much by the controller tool. In other words, you cannot increase speed of the robot using controller tool. This is because robot cannot turn at high speed due to impact of the inertia force. So there is one more thing which must be explained about this controller. This controller assumes that that black circle is always inside red circle. So when you want to run robot fast and accidentally touch the edge of the red circle, robot stops. This is because when black circle touches edge of the right circle, calculations are terminated and zeros are outputted as excess values, and then robot stops. So to continue walking, you need just a little bit move the black circle. So what I want to say is always keep black circle inside the red circle. Don't touch edge of the red circle. Also, I would like to explain what to do if robot falls. So there is red slope in front of the robot now, and this is too steep slope. Robot cannot climb it. So let's see what happens if robot tries. Yeah, I already know it will fall, but anyway. Okay, if robot fell, what you need to do is press stop button, and so robot will return to the initial position, and since Python program is running currently, if you press play button, you will be able to resume your simulations again. So this is basically everything I need to explain about graphic user interface based controller. So please use it if you don't have Sony PlayStation controller. Next, I will move to what I think is main part of my presentation. This is explanation how to program such robot. Title of my presentation states that ROS2 is used for robot programming. So why use ROS2? When using ROS2, programmer must prepare by himself 3 lines of code. These lines are shown on the screen. The first line creates a publisher named publisher which will send data in float64 multi-array format to topic named forward position controller. Here publisher is an optional name. You can use any name you like, and topic name is determined during robot setup. The second line converts joint angle data stored in joint angles array to float64 multi-array format and stores it in the array named pose array. Again here, joint angles and pose array are optional names. You can use other names, any names you like. The third line publishes pose array values. Each time programmer wants robot to move, programmer needs to assign new values to joint angle array elements, convert it using line 2 statement, and publish it using line 3 statement. Then joint angles will be forwarded to the controller and robot will make a move. In other words, when ROS2 is used, programmer's work is reduced to assigning values to array elements. How to determine joint angle values? In this work, trial and error method was used for determining angle values. Wikipedia defines the trial and error method as a fundamental method of problem solving characterized by repeated varied attempts which are continued until success, or until the practitioner stops trying. This approach can be seen as one of the 2 basic approaches to problem solving, contrasted with an approach using insight and theory. Wikipedia explains that the trial and error method is used most successfully with simple problems. So, walk simulation. Is it simple or difficult problem? Is walk simulation simple or difficult? So let's start from analyzing the definition of walk. The definition says, first, the back leg moves forward. Then, on the same side, the front leg moves forward. The pattern then repeats on the other side. The definition shows that walking is a simple phenomenon consisting of 4 leg steps performed one after another. A cycle of 4 steps is completed over and over again. Therefore, the trial and error method can be applied for walk simulation. However, before using the trial and error method, walking phenomenon must be expressed as programming algorithm. Next, I will explain algorithm for simulating walking phenomenon. In this presentation, each leg step is approximated using 5 elemental moves, such as raising leg above the ground, extending leg above the ground, putting leg on the ground, and many others. Approximation of leg steps using the elemental moves is discussed in detail in the videos published on this channel previously. So, to simulate walking phenomenon, programmer firstly needs to set current leg number to 1, and then set current elemental move number to 1. Then programmer needs to define a loop using, for example, until statement, and to specify condition of termination. Then
Programmer needs to set values of joint angle array for current elemental move. Then set delay value. Then publish joint angle array using publish statement, which we discussed previously. Then pause the program execution for duration equal delay value to let robot to complete the move. Then increase current elemental move number by 1. If this number becomes larger than 5, reset it to 1 and increase current leg number by 1. If current leg number becomes larger than 4, reset it to 1. Repeat until condition of termination is met. Condition of termination can be simulation time or number of leg steps or any other. Trial and error method implementation for determining joint angles. Assume that a program for robot walking forward along the straight line is under development. In such a case, we need to specify angles for side joints and angles for shin joints. Angles for leg joints are set to 0 and they are not changed during simulation. Firstly, increase side joint angles with angle for each subsequent elemental move being larger compared to previous move. Make the angle changes small. Run the simulation using the algorithm explained in the previous page. Confirm that robot started to move its legs and that the order of robot steps is as you planned. Next, further increase side joint angles. Confirm that robot maintains its balance and does not fall. Repeat the procedure until robot makes as large step as you planned. When robot step becomes large, you may need to increase shin joint angles to avoid robot tilting its body. Also, you will need to increase shin joint angles when landing robot leg on the ground plane or surface of other objects, for example, slope. After robot starts making large steps, you will notice that despite the steps are large, robot almost does not advance forward. To make robot moving ahead, when one leg of robot moves forward, other legs must push backwards. Push backwards is achieved by reducing side angles while keeping shin angles the same, or in other words, by keeping robot legs on the ground. Again, start from small amount of side angle decrease and gradually make side angles smaller while confirming the effect on robot walk. At some point, you may also need to decrease shin angles also to avoid robot body tilting. After robot starts moving forward, make multiple simulations to confirm that robot maintains balance and does not fall. If robot falls, reconsider angle values you employ. Finally, I would like to explain how to execute the trial program. Download project files using the link in the video description. Open terminal window and launch Isaac Simulator. Using File menu, open Dock Robot USD file. Robot dock and slopes will be displayed. Open another terminal window. Navigate to the directory to which project files were downloaded. Execute calcon build command. Then execute source install setup bash command. Click on the play button and then execute ROS2 launch robot control launch py command. If you have PS4 controller, start simulations. Otherwise, open one more terminal window. Navigate to the directory to which project files were downloaded. Then navigate to UI directory. Execute Python 3 controller.py command. Graphic User Interface controller window will be displayed. Use it as was explained previously. To terminate the program, use Ctrl+C command. Summary. Usage of ROS2 makes programming robot to walk as simple as assigning joint angle values to array elements. In its turn, joint angle values can be easily determined using trial and error method. Robot dog was programmed using trial and error method, and robot capabilities were demonstrated. The developed program is offered for trial.